Hello and welcome to the lecture for 7.3 Trigonometric Substitution. And this entire section is going to pose a question involving integrals that look like this, where we have a radical with a function like this underneath it, and we can't substitute that function as there's no derivative of that function next to it. So we're gonna talk about that and just see what we can do to solve this problem. Well, from the title, you can already know that we're gonna do some sort of trigonometric substitution. So I'm just gonna begin by kind of deriving our first method here, which is the sum of our variable and our constant. So let's go ahead and look at this. So x squared plus a squared. So this looks a little familiar. This will probably look a little bit like the square root of a squared plus b squared, Pythagorean theorem, which equals r. Might look a little bit like this. Excuse the handwriting here. And, well, okay, so let's just kind of keep going through this. Well, the sum of these two. So r is going to be defined as the sum of two legs. So we know that this. So this is a sum of legs, right? We have our sum of these two legs right here. Okay. So we know that, so we have both of our legs here. Now there is, this is going to be legs of a triangle, by the way, a right triangle at that. And we know that these two legs are here, so we know we have two legs. So as it's the sum of these two. So we need to know what appropriate trig function to use to substitute into this because based off of this information. So we need to just kind of look at, so I'm going to use darker blue here, so tangent theta equals y over x. Ooh. Y over x sine theta. I am sorry, this pen is kind of but I'll try my best to work with it here. Equals y over r cosine theta equals x over r. So we have both legs here, so we're probably going to end up using tangent here. So, okay, well, why don't we substitute x for tangent? So we want to do this in a way where we have x over, so x here plus a squared. So we want to do this in a way to where we get tangent from the triangle. So this will be y over r, so why don't we have x over a, and then this will be the square root of x squared over a squared, plus a squared. So a lot of the setup comes from the triangle method here. You can do this without a triangle. In fact, I believe Dr. Barron teaches it without the triangle. I do it with the triangle as I find it easier to figure out some things, especially whenever you're at the end of evaluating these. So, okay. So we're going to do this in a way so that we get x over a. So tangent theta equals x over a. And we want to do this in a way so we can substitute for x. So we're going to multiply a on both sides. So multiply a on both sides, we're going to get a tangent theta. So that equals x. Now keep in mind, whenever we substitute here, there is a particular way you're going to substitute here with your differential, because your differential is going to change from dx to d theta. And whenever that happens, the way you substitute with trig sub, it's a bit different. You're going to take the derivative of this function that you're substituting for, and you're just going to stick this on the end of it. So you're going to do a secant squared theta d theta, and that's going to be your new differential right there. So it changes a little bit. It's a bit different than what we've done before with regular trig integrals, but it's a little intuitive. Just keep in mind what you're doing here. So let's go ahead. I'm going to just kind of substitute. I'm going to do this in green so you can see that what our final result looks like. So square root of, so it looks like this is going to be a squared tangent squared theta plus a squared, and then secant squared theta d theta. So forget the a there. Don't forget that a. You have to bring that constant there. And what we know from this, move this over to the side a little bit, is we can actually pull out this a squared. And then you'll see what the end goal is. So we're going to factor out that a squared. And we get something rather convenient here where we can actually bring out that a. So it's going to go from a squared to a. So tangent squared plus 1. And we can actually use an identity here. And then we're going to use secant squared theta as they're equal to each other, right? So the final integral we're going to get is going to be a secant theta a secant squared theta d theta. So this is the kind of integral we're trying to work towards right here. So we're trying to work towards something that looks like this, because we can integrate this. We can integrate this via most likely a substitution, as we have a derivative right here. So let's do like an actual example. I'm going to switch over to whiteboard, as whiteboard is just better for doing this kind of stuff. And so if you're ever working with like digital pens or anything, whiteboard is really good for working in problems, working problems out. So let's start with an integral. It's going to be 1 over x squared plus 1 to the 3 halves dx. So this is going to be a little similar to what we just did, except we're actually working with values now. So look at this. We have a sum, tangent theta. So whenever you see the sum of these, you're going to use tangent theta. This specific example is going to be with tangent. The next video I do will probably be with secant and sine, but this is mainly set up so we can actually do these integrals with tangent and kind of give you a general idea of what we're doing here. So Okay. So let's go ahead and draw the triangle out. Sorry, my triangle sucks. I'll redo that. That's not much better, but we'll keep it. So x over a, we're going to have x over 1 over the square root of 1 plus x squared. So we're going to want x over 1 equals tangent theta, x equals tangent theta. This is good. We don't have to do much setup for this, which is awesome. Okay, so I'm going to evaluate this in green. So we're going to have tangent squared theta plus 1 to the 3 over 2. And then don't forget our derivative. So dx, our differential, is going to equal secant squared theta. Remember, our constant was a, so that's why there's no constant here. I mean, our constant was 1. And then that's our integral right now that we're going to work. Okay, well, plug in an identity here. And you might notice a pattern here with what we're doing, and I'll elaborate more on that in a second. So, plugging that in, so we're going to have secant, so what we're having here is secant squared theta times secant squared theta to the 1/2. And we're going to get secant cubed theta. So let's rewrite this, secant cubed theta, secant squared theta, d theta. And we can actually cancel out the secant squared and this cubed. So boop, boop. And now we're going to have the integral of 1 over secant theta d theta, which actually equals the integral of cosine theta. And evaluating this, we're going to get sine of theta. No plus c yet, as we have one more step to do. We have our original function. Oh, that's Calc 3 stuff. We have our original function in terms of x, so we want the answer in terms of x. So we're going to work with this a little bit. So sine is y over r. So we're going to have x over the square root of 1 plus x squared. So this is going to equal x over the square root of 1 plus x squared plus c. And remember that sine equals y over r. This is why I draw the triangle, because I can visualize this better. So, and that is our answer right here. So I'll conclude this video to show just kind of a setup of what we're going to be doing with this in the next video or two. Next video will be on secant and sine, and the one after that will be about a little bit more complex ones where we have to, where we might have to do something like completing the square and then doing a substitution and then doing a trig substitution. but this is just the foundation of what we're going to be doing in the next 2 videos. So I'll see you in the next one.